Hello friends, in this video we are going to see the numerical based on the cooling load estimation only. Only the thing in this particular numerical, along with the sensible heat and latent heat, infiltration load is only given. Okay, other than infiltration, nothing else load is given. So whenever only infiltration load is given and sensible heat and latent heat is given, then how to solve the numerical, that we will see in this particular video. So here is the statement given. The following data refers to air condition hall. Outside conditions are given as 38 C dBT and 28 C WBT. Then room conditions are given as 24 C dBT and 60% RH. Sensible heat is given 1,67,040 kJ per hour. Latent heat is given as 41,760 kJ per hour. Infiltration is given over here at least 20 cmm. So now this infiltration is nothing but what? Actually they have given the volume flow rate of the infiltrated air. Okay, from this we are supposed to get the mass, and from the mass we are supposed to get the sensible and latent heat because of the infiltration. Okay, then ADP is given over here. Then they are saying that 60% of total air is recirculated and mixed with the conditioned air after the cooling coil. So it is 60% of total air is recirculated. So return air is 60%. Obviously remaining 40% will be the fresh air. So we are supposed to find out what is RSHM, WBT of air leaving the conditioner, relative humidity of air entering the hall, enthalpy of air leaving the conditioner, enthalpy of air inside the room, cooling coil capacity, all those things we are supposed to find out. So first what we will do, we will try to draw the schematic of this particular diagram, schematic of this particular numerical. Fine. So assume that this is what the room which is to be cooled, or the hall actually, which is the condition hall. Okay, so this is the hall. Then I'm having what, the conditioner over here, or the air handling unit, you can call anything over here. I'm just calling this as the HU, which is having one cooling coil over here. This is the cooling coil. Okay, assume this is the cooling coil. Then you have the blower over here. Okay, now obviously front side of the blower will be the supply of air to the room. So this is the supply, this is the supply, and from room the air is taken back over here. So this is the return, this is the return. Now as per the statement, as the mixing is after the cooling coil, so this is the cooling coil, so the mixing will be somewhere over here. So obviously I need to connect this particular recirculated air or the return air over here after the cooling coil. Somewhere over here I am having the fresh air, so this is the fresh air. Okay, I will call this fresh air as the point number 1, room as the point number 2 over here. Okay, then obviously when this fresh air is passing over the cooling coil, when the fresh air which is at the state number 1 is passing over the cooling coil, immediately after the cooling coil, before mixing, because mixing is at a distance from this particular cooling coil, it won't happen like that the air is coming, return air is coming, and immediately after the cooling coil will have the mixing. It is not something like that. There will be a small distance between the return air and the mixing section and the cooling coil. So immediately after the cooling coil, obviously the state will be different than the state number 1 over here. So 1, 2 already I have taken, so I will call this as the state number 3, which is immediately after cooling coil, and this air which is at the state number 3 will get mixed with the return air which is at the state number 2, and that mixing point, let's say call as the point number 4. Okay, so this point number 4 will go to the blower, and from blower it will be supplied to the room. So obviously point number 4 will be the supply point over here, and the point number 2 will be the return point over here. Okay, so this is what the schematic of the problem. So once you are through with the schematic, half of the problem is clear to you. Okay, it's very important to draw the schematic first of all. Now we just will go on noting down the given data over here. So outside conditions are given 38 C dBT, 28 C WBT, so that we can directly plot on the psychrometric chart. Room conditions are given as 24 C dBT and 60% RH. So I am maintaining this room as 24 C dBT and 60% RH. Okay, that is what the condition of room is given. We don't know what is the condition of this particular mixed condition and immediately after the cooling coil. ADP is given over here, that is 10 degrees Celsius. Fine. So the first thing they have given, what are the data given over here? So here I can write given data, the sensible heat they have given, as 6, what is that, value is 1670 and 40 kilojoule per hour. Convert this to kilowatt, kilojoule per second, and by dividing it by 3600, we are supposed to convert this hour to second. So I'll multiply this particular one into 3600. So obviously 1670/40 divided by 3600. So it is 1670/40 kilojoule divided by hour. I'll convert it to second, 3600. The value will come around to be 46.4 kilowatt. This is the sensible heat, 46.4 kilowatt. Similarly, I'll calculate the latent heat, okay, which is equal to, they have given as 41,760 kilojoule per hour, which is equal to, again by using the same, I will just divide it by 3600. I will get this value as 11.6 kilowatt. Now they have given the volume flow rate of infiltrated air, okay, which is 20 cmm. So 20 cmm is nothing but 20 cubic meter per minute. So it's a 20 meter cube per minute. That is the value given over here. Right. Now I'll make use of the the psychrometric chart to find out what the volume flow rate of the infiltrated air. So the step something like that. Now I know the sensibility and latent heat, but this is not the total of the room sensibility and room latent heat, because they have given the infiltrated air. So because of this infiltrated air, there will be sensible heat due to infiltrated air, as well as latent heat due to infiltrated air. Okay, and finally I'll have the room sensible heat. Formula will be given sensible heat plus sensible heat due to infiltrated air, because there is no any other parameter given or the factor given, so only sensible heat due to infiltrated air. And we know that because of the infiltration, sensible as well as latent, both the heats are getting added to the room. So sensible heat plus sensible heat due to infiltrated air, and the total room latent heat will be latent heat plus latent heat due to infiltration. Okay, so this value, sensibility and latent heat, I am having, that is 46.4 and the 11.6. okay, but I don't know what is the value of sensibility due to infiltration and latent heat due to infiltration. So that we will find out. So I am writing over here, that is the infiltration load. Obviously I need to make use of the psychrometric chart. So here what I supposed to find out, the I supposed to find out the mass of infiltrated air. Okay, and from that mass I will calculate what is the sensibility and latent heat over there. So we will go to the psychrometric chart over here. Fine. So here the conditions are given as outside conditions are given as 38 and 28, 38 degrees Celsius and 28 degrees Celsius. So 35, 36, 37, 38. So this line, okay, 38 and 28, 25, 26, 27, 28. So here this is the line. Okay, so this line is of 40, correct, 40, 38, I say 39, 30. Somewhere over here I will get this particular point. This is the point number 1. Okay, on the psychrometric chart. Now I need to get the point number 2, which is 24 C dBT and 60% RH. This is 40, so 50, 55, 60. Okay, so this is the point number 2. This is the room design condition. So if I connect this to, this is the point number 1 to 2, basically process 1 to 2. Okay, now here I'll plot the enthalpy. So with respect to point number 1, the enthalpy is just a minute. This is 25, 26, 27. Sorry, this is 28. This is 28 and 30. I'll do it once again. Just a minute. I will do it again. By mistake I plotted the point number point number 1 wrongly over here, so that this type of mistakes can be happen in the exam as well. 25, 26, 27, 28. So this is 28 and 38. So this line is of 40, 39, 38 and 28. So this is the point number 1. Fine. Now it is okay. The point number 1, I will join 1 to 2. So with respect to point number 1, if you see the enthalpy is 90, it is 90. Okay, so I will just note down that value. So here I'll write H1 is equal to 90 kilojoule per kg of dry air. Now we will see what is the enthalpy at point 2. So this is H2, I'll just plot it over here. So it is about H2 is about 52.5. okay, sorry, H2 is 52.5 kilojoule per kg of dry air. Okay, now I will have one vertical line over here and one horizontal line over here. So this is already we know that this is the intersection point. I will mark as the point number. So this is what the line. This is the point number A. This is the point number A. Now we know that infiltration is nothing but outside air is directly mixed with the room air. So outside condition is 1, mixed condition is 2. So outside condition is directly mixed with the room condition. So because of this particular process, what amount of sensible heat will be added and what amount of latent heat will be added over here. So if you see this particular diagram, we know that the horizontal line over here, which is at the constant with W or the specific humidity, this is nothing but the sensible heat. This is nothing but the sensible heat. This 2 to A is nothing but the sensible heat. Now this sensible heat is because of the infiltration, because the infiltration process is from 1 to 2 outside air to the room air. Okay, so this is the sensible heat, H2 to HA, and 1 to A, this is nothing but the latent heat. 1 to A is nothing but the latent heat, because this is at the constant dry bulb temperature. Now obviously if I get the enthalpy difference over here, HA minus H2, I can find out the sensible heat. So that sensible heat will be nothing but what? So if I want to write the formula for sensible heat, it will be HA minus H2. However, the unit for this will be kilojoule per kg. So I need to multiply this particular term by mass of air, mass of infiltrated air, because this is the infiltration sensible heat. So I will multiply this by mass of infiltrated air. Then I can get this particular value in kilojoule per second, where the mass will be in kg per second. Okay, so this is how I can find out the sensible heat due to infiltration. Similarly, if I want to have the latent heat due to infiltration, so it will be mass of infiltrated air into H1 minus HA. This is the latent heat. Fine. So for that I need to have the enthalpy of point A over here. Okay. So if we go by this, we can find out the enthalpy of point A is about 68. If we go by this, we'll have this enthalpy about 68 over here. Fine. So I'll just mark that. So HA is nothing but 68 kilojoule per kg of dry air. Okay. Now the sensible heat due to infiltration. So as I already written the formula, sensible heat due to infiltration, which is nothing but mass of infiltrated air into enthalpy difference, that is HA minus H2. Where I don't know what the mass of infiltrated air that I supposed to find out, and we know that the mass of infiltrated air, which is nothing but, because I know the volume flow rate of infiltrated air. Okay, so this will be volume flow rate of infiltrated air divided by the specific volume of infiltrated air. Okay, now specific volume is nothing but at what point the infiltrated air is getting in. So it is getting in at point number 1. Okay, so with respect to point number 1, what the specific volume, and the specific volume I can get it from the psychrometric chart only. So these lines, these slant lines, dark slant lines are for the specific volume. So this is nothing but the 0.9 kg of 0.9 meter cube per kg of dry air. So this is 0.9. This is the 0.92 because there is a difference of 0.2 over here. So 0.88, 0.9. So this will be 0.92, and in between if you see the point number 1 is there. So the specific humidity, specific volume with respect to point number 1 is about 0.91. It is about 0.91 meter cube per kg of dry air. Okay, so here this particular specific volume with point number 1 with respect to point number 1, or specific volume infiltrated air is 0.91. So therefore I can get the mass of infiltrated air, that is this 20 meter cube per minute divided by 0.91. Okay, so obviously this unit will be meter cube per minute, and this is meter cube per kg of dry air. So finally this meter cube get cancelled. I will have this particular mass of infiltrated air as about 21.98 kg of dry air to the minute. Okay, kg of dry air per minute. Obviously I need to have this particular answer of sensibility in kilowatt. So if I put the mass in kg per minute, if I let's say put the mass in kg per minute into the unit of enthalpy is kilojoule per kg of dry air, or kg, I'm just writing kg. So kg get cancelled, you will have the unit as kilojoule per minute. So this is not the kilowatt. So I want to have this answer in kilowatts. So I will convert this mass which is in kg per minute, I will convert this to kg per second, and the answer for this kg per second is about 21.98 divided by 60. You will have 0.37 kg of dry air to the second. See, kg of dry air or kg, one and the same. I am just writing for simplicity, or to save the time, I am writing the kg. Okay, so it is 0.37 kg per second. Now you can easily find out what is the sensible heat due to infiltration. So it is sensible heat due to infiltration. It is 0.37 into enthalpy at point A is 68 minus enthalpy at point 2 is 52.5. Okay, so this is coming around to be, if you do the calculation, 0.37 into 68 minus 52.5 is about 5.68 kilowatt, is about 5.68 kilowatt. Fine, so this is the sensible heat due to infiltration. Similarly, I will find out the latent heat due to infiltration. Latent heat due to infiltration. So once I get the sensible heat and latent heat due to infiltration, I can finally find out what is the total room sensible heat and total latent heat. So again this formula is same, mass of infiltrated air into, I will consider the enthalpy difference for latent heat, and that is nothing but H1 minus HA. If you see the psychrometric chart, H1 to HA is the latent heat. So H1 minus HA, fine. So again you put the values over here. H1 is 0.90, HA is 68, okay, and mass of infiltrated air is 0.37 kg per second. If you put all these values, you will get the latent heat due to infiltration is about 8.14 kilowatt. Latent heat due to infiltration. Fine. So from this I can find out the room sensible heat, which was the formula as written as sensible heat plus sensible heat due to infiltration, because there is no any other parameter or the factor given like solar heat due to infiltration or the occupancy. Those things are not given, so we will not consider. If it is given, then I need to add those as well. That we have seen in one of the problem, one of the video is there based on that. So you can go through that video. So there you can come to know that if the parameters are given like solar heat gain, occupants heat gain, then those parameters also I need to consider over here. Okay, but those things are not given in this particular problem, so I am not considering that. Whatever is given, that only I will consider, that is the sensible heat due to infiltration, or the infiltration load is given, so I will find out sensible as well as latent, because due to infiltration both the heats are getting added, sensible as well as latent. That already we have seen in the previous videos. Okay, so sensible heat plus sensible heat due to infiltration. Sensible heat was 46.4 kilowatt plus this is 5.68. So finally I will get this particular sensible heat is about 52.08 kilowatt. Similarly, the room latent heat is nothing but the latent heat plus latent heat due to infiltration. So that is about latent heat was given as 11.6 plus this is 8.14. So this final answer will be 19.74 kilowatt. So from this I will get the first answer, which is nothing but the RSHF, which is equal to room sensible heat divided by room sensible heat plus room latent heat. So this is, if you put all the values, you will get this answer as 0.725. Okay, this is the one of the answer they have asked. RSHF, that is 0.725. Okay, so we are through with the RSHF. Now they are asking what is the WBT of air leaving the conditioner. So whose WBT we are supposed to find out? The leaving the conditioner, what is the state? That is the point number 3. So with respect to point number 3, I am supposed to get what is the wet bulb temperature is. So for that I need to have the point number 3 over here. Now we know that process 1 to 3, that is from process 1 to 3, that process is the cooling coil process. That process is cooling coil process, and this cooling has to be done up to the apparatus dew point temperature of the coil, which is nothing but the ADP of the coil. Okay, the ADP is given over here, that is 10 degrees Celsius. So obviously I need to extend the process from point number 1 up to the ADP, and on that line somewhere over there I will have the point number 3. Fine. So likewise I will do. So what I will do over here, first I will draw the line from point number 1 to ADP, from point number 1 to ADP. So ADP is given over here, that is 10 ADP. Okay, so I will just draw this particular line. As of now I am just connecting this particular line. Okay, fine, but I don't know what is the supplier point, or that is rather the point after the immediately after the conditioner, that is the point number 3. So somewhere on this particular line I will be having the point number 3, and to get the point number 3 I suppose to have the RSHF line, because this line is nothing but the GSHF. This line is nothing but the GSHF line. So intersection of GSHF and RSHF is nothing but the condition after the cooling coil, or the supply condition. Okay, so point number 3 is one of the supply condition if you see the schematic. So I can call this GSHF and RSHF intersection is the condition after the cooling coil. So I supposed to get the RSHF line, and we know the procedure for getting the RSHF line. Already we have calculated the RSHF, that is 0.725. So somewhere over here I am having the RSHF. This is the RSHF. I will connect this RSHF with the alignment circle over here. I am just connecting over here, something like this. And to this particular line, this line is known to be the base line, correct? To this particular line, I will draw a straight line from the room design condition. I will draw a straight parallel line to this particular baseline from the room design condition. So room design condition is the point number 2. So from point number 2 I will draw this particular parallel line to this particular baseline. So something like this, I will have this line. Okay, something like this. Okay, this is nothing but the RSHF line. Now the point of intersection of RSHF line and GSHF line is the point which is nothing but the after conditioner, which is nothing but the point number 3 over here in our case. This is the point number 3. Okay, so this point number 3, again I am telling, to get the point number 3 or the condition after cooling coil, you have to have the point, this particular RSHF line and the GSHF line intersection, you will get the point number 3. So now we'll go back to the statement, WBT of air leaving the condition. So I am supposed to get the WBT value with respect to point number 3. Okay, so with respect to point number 3, if you see the WBT, it is coming around to be, so this is 10, 11, 12, 13, okay, somewhere about 14 we are getting this particular answer. Okay, so that is the answer. Obviously I am not drawing that particular value or the line with the scale, so I will get some difference. So I will have WBT immediately after condition, that is at point 3, which is nothing but about 14 degrees Celsius. Okay, you can check your answer on the cyclomatic chart directly. Fine. Okay, what else they have asked? That is RH of air entering the hall. Okay, so this answer is also okay. Relative humidity of air entering the hall. So what is the point which is entering to the room? That is the point number 4. So I supposed to get the point number 4. Point number 4 over here, and with respect to point number 4 I will get the relative humidity. Now point number 4 is the mixed point which is the mixing of point number 2 and point number 3. So we know that we have let's say if I am having the mixing before the cooling coil, let's say this is the HU and this is the air coming from the room, this is the point number 2, this is the fresh air. So we know the formula. So this is the fresh air M1 upon M2, which is equal to H3 minus H2 divided by H1 minus H3. That was the formula when the mixing is after cooling coil between 1 and 2. Now I am having the mixing between 3 and 2. I am having the mixing between 3 and 2. So what I will do, I will use the same formula but for the 3 and 2. Okay. So here the M1 will be replaced with M3. So this is M3 divided by M2 as it is, which is equal to instead of H3 now the mixing point is 4 because 3 is the mixing point over here. So here it is point number 4. So it will be H4 minus I will have the value as H2 divided by, now instead of H1 I need to use the H3 minus H4. The mixing point is 3 over here, 3 over here, here it is point number 4, so it is H4. So by using this particular formula you can get what the enthalpy of point number 4. Okay, so I am just writing that particular same formula over here. So let's say I'll just do something like this. So M3 upon M2, which is equal to H4 minus H2 divided by H3 minus H4. Okay, so from here now I know what is the H2 value. So enthalpy at point number 2 already we have noted down, it is 52.5, and H3 enthalpy, yes, H3 I will just get it from the psychrometric chart because just now we have got the point number 3. So with respect to point number 3, the enthalpy is about it is 40. If you see, it is about 40. Okay, so I will have this particular enthalpy or whatever 38, whatever the answer you are getting. So assume that I'm for simplicity I am considering the 40 over here. Okay, so this is the 40, something like this. Sorry. Okay, so it is about 40. Fine. So H3 is 40. Put the values over here. So M3. Now what is M3 over here? M2 is 60%. So this is 0.6. Obviously the remaining 0.4 is nothing but the M3. So 0.4 divided by 0.6 is equal to H4 is unknown minus H2. What is the value of H2 is 52.5. 52.5 divided by H3 is 40 minus H4. If you solve this, by solving this you will get the enthalpy at point 4 is about 47.5 kilojoule per kg of dry air. So this is the enthalpy at point number 4. So by using this enthalpy I will plot the point number 4 on the psychrometric chart. So it is 47.5 somewhere over here, 45, it is 47. So I'll just draw this particular line from 47.5, something like this. Wherever it is intersecting to this particular line 2 to 3, because the mixing is between 2 and 3, correct now? So wherever this line is intersecting to 2 and 3, I will get the mixed point, that is a point number 4, mixed point number 4. This point number 4 is nothing but the supply air condition. Point number 4 is nothing but the supply air condition. So now we will go what is asked. We will just see relative humidity of air entering the hall. So with respect to point number 4, find out what is the relative humidity. So it is this is 65% and this is 65 70. Okay, so if you see the relative humidity is about we are getting about 68-69. Okay, so I can write the relative humidity at entering the air, that is point number 4, let's say it is about 69%. Okay, it is about 69%. Okay, so 69 to 70 or 71 you'll get. So based on your chart, on the parallel lines you are drawing, you will get this particular value over there. Fine. So this is also we have found out relative humidity of air entering the enthalpy of air leaving the conditioner. So obviously, what is the enthalpy of this? Enthalpy of air leaving the conditioner. So when it is leaving the conditioner, the state is state number 3. So with respect to point number 3, what is the enthalpy? So just now we have noted somewhere. So enthalpy, yes, this is what the enthalpy. This is the what enthalpy after conditioner, immediately after conditioner. So that is 40 kilojoule per kg of dry air. Enthalpy of air inside the room. So inside the room, what is the state? That is the point number 2. That is the point number 2. So don't get confused over here. Inside the room, the condition is point number 2, not the point number 4. Point number 4 is the supplier condition. So inside the room, the point is point number 2. So with respect to point number 2, what is the enthalpy? That is the H2. That is the H2. So this is the next answer, 52.5. Okay, to confuse you, this will ask. Okay. So enthalpy of air inside the room is H2. So this is nothing but the H2, which is equal to 52.5 kilojoule per kg of dry air. Then cooling coil capacity. Okay, I will find out the cooling coil capacity. So somewhere over here we will find out cooling coil capacity. Okay, so to get this cooling coil capacity, I will go back to the schematic because I need to see what are the points across the cooling coil. So across the cooling coil, this is the diagram for our numerical. So across the cooling coil, the points are point number 1 and point number 3. Okay, so obviously I need to get the enthalpy difference between 1 and 3 so that I can get the cooling coil capacity. So the formula for this cooling coil capacity will be H1 minus H3. Obviously this answer will be in kilojoule per kg of dry air. So I need to multiply this particular term by mass of air which is supplied to the room. Okay, mass of air which is flowing over the cooling coil. Extremely sorry, it is the mass of air which is flowing over the cooling coil. Now if you see the this particular schematic, the mass of air which is flowing over the cooling coil is the mass of fresh air. It is the mass of fresh air. Okay, so to get the cooling coil capacity, I need to multiply this particular enthalpy difference by mass of fresh air. By mass of fresh air. Now I don't know what is the mass of fresh air over here. Okay, so to get the mass of fresh air, I will find out first what is the dehumidified air, what is the total air supplied to the room, because out of that total air 60% is return and 40% is the fresh air. Okay, so total air supplied to the room, total air supplied to the room, supplied to room. Okay, that also I can call it as a dehumidified air. Okay, dehumidified air, because the air which is supplied to the room we are calling as the dehumidified air, and that I'll mark as the mass of dehumidified air, that is MD. Okay, obviously now we'll go back to the schematic again. Whatever mass I'm supplying over here, that is the MD, that mass is responsible to take the heat from the room, Okay, so whatever total heat is generated inside the room, that heat will be absorbed by the air which is supplied at the point number 4. Okay, and the enthalpy is getting changed from the point number 4 to point number 2 of that particular supplied air. Okay, so it is nothing but whatever heat is generated over here, that heat will be absorbed by the air which is supplied over here. So I can write the formula over here. The heat generated in the room, is nothing but the heat absorbed by dehumidified air. Okay, so what is the total heat generated inside the room? That is the room sensible heat plus room latent heat, that is the total heat generated. And what is the heat absorbed by the dehumidified air? That is what is the mass of dehumidified air into the enthalpy difference across the room, because that particular air is supplied at point number 4 and getting returned at point number 2. So between 4 and 2 there is the enthalpy difference happening over here in the air, correct? So I need to consider that enthalpy difference as H2 minus H4, which is nothing but the across room, H2 minus H4. Okay, now here I know what is the room sensible heat and room latent heat. So what that already we have calculated 52.08 and 19.74. Okay, so 52.08 plus 19.74, which is equal to MD. I don't know, I will get it. H2 is 52.8 minus H4 is 47.5. So from this we can find out what is the mass of dehumidified air. Okay, from this we can find out the mass of dehumidified air. Okay, I'll just do the calculation over here for mass of dehumidified air. So it is 52.08 plus 19.74 divided by 52.8 minus 47.5. So that mass is coming around to be 13.55. It is 13.55 and the unit is kg per second, because this value is in kg, kilojoule per kilojoule per second, or the kilowatt. This value is in kilowatt, so kilojoule per second. This is kilojoule per kg, so kilojoule will get cancelled. Finally I will remain with kg per second. So mass of dehumidified air will be 13.55 kg per second. So from this mass of dehumidified air I can find out the mass of fresh air, which is nothing but the 40% of total dehumidified air. So it is 0.4 of md, which is nothing but 0.4 of md, and the answer for this will be, I'll just multiply this particular term by 0.4 and it is around coming around to be 5.42 kg per second. So this is the mass of fresh air. Now you can put this value of mass of fresh air in this particular formula, okay, and then you can get what is the cooling coil capacity. Okay, so that is 5.42 into just a minute, into enthalpy at point number 1 was 90. Okay, it is given over here, it is 90. See, here it is 90, and enthalpy at point number 3 is 40. Okay, so 90 minus 40, so it is coming around to be 271.01 kilowatt. This is in kilowatt. Convert this value of kilowatt to tons, so we will just divide this particular entire term by 3.5, because 1 TR is equal to 3.5 kilowatt, and that answer is coming around to be 77.43 tons of refrigeration. So this is the cooling coil capacity, 77.43 TR. Okay, so this is how you can solve the numerical based on the infiltration load. Only infiltration load is given, and here additionally they have given the cooling is after the conditioner or after the cooling coil. That was the only change over here. So this is how you can solve the problem. Fine. Thank you. If you are having any doubt, any issue, you can write down into the comment. I will try to solve those. Fine. Thank you guys.